car, there's the computing platform has to process information fast enough. And the sensor information is coming in from all over. You've got, of course, the simple stuff like GPS and the IMU and the rotation of your tires and your steering wheel. You also have the cameras that are coming in all around you. You have LiDARs, you have radars. And then now, as you heard from Alon, we also have HD map. All of this information is fused together as the input information into your car's operating system. And this information is being changed and updated and ingested in real time. This is the ultimate real-time, high-throughput supercomputing problem. And you've got to get that job done. You've got to get that job done. Best effort is not enough. It is not enough that when you hit enter, it says, you know, I tried. I just wasn't able to detect it in time. Next time, when the car is not traveling so fast, I will be able to detect it in time. It has to be high throughput. It's got to be mission critical. The algorithm for basically driving self-driving cars, the basic functionality I described, there's sensing, there's localization, there's planning, and there's the action taking. What I want to show you today is this. This is our operating system. The operating system is much, much more than this, but I want to show you the algorithms part of the operating system, and I want to show you an update of where we are. Basically, the way it works is this. The sensor information is coming in on the left. We have 3 artificial intelligence networks running on this car. 3 deep learning algorithms. The first one is just detecting things. We detect cars, we detect lanes, we detect signs, we detect cones, we detect things. We detect things, okay? It's called DriveNet, we detect things. As it turns out, none of us drives like that. None of us drive by going, no cow, no dog, no person, no car, no cone, no tree, no lake, what are all no house, no truck, the list could be pretty long. It would be a debilitating way to drive. We detect these things for 2 reasons. One, we want to continuously update our HD map in the cloud. And there are several different markers that we see that can help us figure out where we are. Number 2, as a backup, just in case, as a backup. But the real way of driving is this. You detect what's safe to drive. When you're driving, you're detecting, look at that, it's a road, it's safe, look, it's open. There's nothing inside. The absence of things is open road. There's a network that is doing segmentation and figuring out where is it safe to drive. Not what not to hit, but where is it safe to drive. However, it turns out there's even a third network, and really the way that we drive. When we're driving, we're not thinking at all, unfortunately. When we're driving, it's just a behavior like playing tennis. It's a behavior. You simply grab the steering wheel, you start driving. All of the sensory information comes in, your brain is thinking, it's working, and it's doing completely by reflex, and we just drive. And that's one of the reasons why we can listen to a book while we drive. That's one of the reasons why we can have a conversation while we drive. When we're driving, it is a behavior. We have a third neural network called Pilotnet, and it's simply a behavior network, okay? Not a detection network, a behavior network. So the first thing is this. The first section is we detect everything around our car. We create one of the most important data structures of self-driving cars called the occupancy grid. The occupancy grid is a 3-dimensional grid that's being updated completely in real time with all of the sensor information, all the detection networks, and it's creating this 3-dimensional mesh of your world. It's creating a virtual world. This is the virtual mathematical world based on all of the sensor information that it has accumulated. It's called the occupancy grid. That occupancy grid is, if you will, the primary asset, the database of the self-driving car. That occupancy grid then is tested against what the car would like to do. The car is driving by itself using Pilotnet. It's going to go and start driving based on just what it sees. We're going to tell it, go in that direction, it's going to go. It's going to start driving based on everything that we taught it, And it's going to be tested against the future prediction of everything around the car. And if we were to hit something or the path would lead to a collision in the future, in the near future, we would, of course, override it. Okay? So, and then what we do is because we would like to test that our understanding of the world is consistent with the understanding of the car. That our understanding of what we see is consistent with the understanding of the car. We visualize the occupancy grid in a virtual reality, if you will, computer graphics of what the car sees, the artificial intelligence car sees. And so let me first show you the upper left-hand corner, just detecting things. Justin, please. This is in California. We're detecting things. Now, when we detect, this is our latest net. We're going to detect three-dimensional objects, because a car, as you know, is not a flat image. So we have to detect what we think is the volume around the car. Okay, and all of that information now gets included into our occupancy grid. We would also like to know where the lanes are. Okay, we'd like to know where the lanes are. We would also, those are our easy things. We would also like to know where is it safe to drive. Now this is really cool. Look at this. It's looking at the scene and it's saying, you know what? You see the yellow? All the yellows, the red, passenger, not safe. Yellow, not safe. Red, not safe. Blue, safe. You see this? Okay. Red, it recognizes pedestrians. Not safe. Please do not go there. Does that make sense? You see that? Red is pedestrians, yellow are cars. Okay? And it's simply looking at every single image and saying, where is it okay to drive? Where is it okay to drive? I don't necessarily drive there, but where is it okay to drive? First of all, where is it okay to drive? And when I'm, of course, driving, this is what I would see. Now, of course, I would never go into the other lane because I know the rules of the road. But otherwise, I can pretty much drive in the areas that is safe to drive. Now, let's put it all together, Justin. And so we got detecting the cars, detecting the lanes. It's running on the Drive PX computer, the operating system called DriveWorks, and it's detecting these things, okay? Now, these things are all getting put into the occupancy grid, as I mentioned earlier. Let's go back to the slides, please. Okay, so you saw all these network detections. We take what I'm going to show you now is the occupancy grid. However, before you can have the occupancy grid, you have to have the HD map, in this case from TomTom, and it tells us where the lanes are, it tells us where the signs are, and based on our ego motion, which is the motion of the car, we figure out where we are on the road. It's called localization, okay? It's a very simple version of reasoning. The car's reasoning about where am I in the world? And so let's show people what the car sees. Okay, so this is our digital dashboard. This comes off of Drive PX2. As you know, one of the things that we do very well is computer graphics. I've had people look at this and they go, wow, it's amazing, the graphics you guys can do. And I said, I know, thank you. We learned it recently. It turns out that the computer graphics you're seeing here is actually quite remarkable. This team of young engineers over here, Justin, won't you? Come on, you guys, stand up, take a bow. I know you haven't slept. Thanks, guys. It's amazing what you could do on caffeine alone. It is, you know, whereas deep learning is the fuel of artificial intelligence, caffeine is the fuel of deep learning engineers. And so what you're looking at, this is the occupancy grid. This is the mind of the computer. This is literally the data structure of the computer. Okay? This is the data structure of the computer. And so figured out where it is in the lane. These are the cars next to it. Can you guys see this? And we're detecting the cars and tracking the cars in 360. Justin, does it make sense to show the front video? Did you want to do that?
Sure. Yeah, the video, or we can also enter into sort of a auto cruise mode where the car's driving itself like that.
Okay, so when we're in auto cruise mode, the digital dash changes pretty dramatically to let us know that it is in auto cruise mode.
Yeah, it's got to be a big change.
Yeah.
Yeah, absolutely.
So now these are all the cars that we detect. Notice the cars in front of us, we're detecting these cars. Okay? So you see the cars. And so what's happening here is we're detecting, we're localizing, connecting to the HD map. We create an occupancy grid, and this is the visualization of the occupancy grid. When you look out the window and it's inconsistent with this, then you know that something is wrong. I would go back to manual mode. File a bug with NVIDIA. Okay? And we'll get on it right away.
Yeah, and it's so much more sophisticated and difficult to represent this full 3D space rather than just some bounding boxes. So this really represents really advanced deep learning to be able to identify the exact locations of all of these.
Right.
Yeah.
And so really what Justin's saying is by recognizing the bounding boxes, we know the extent of that car in the occupancy grid. It could be a little tiny Mini Cooper. It could be a super, super long truck.
That's right.
Right? Okay, so visualization of the occupancy grid. Now let's come back to the slides, please. All right, so what you saw earlier is detection, and then you saw us, you didn't see the occupancy grid, but you saw the visualization of the occupancy grid, which is in this UX, which I think is going to be pretty important to the future of self-driving cars, actually. You want the driver, you want the passengers to know that the car has the situation in hand, and you want to be able to calibrate against where it wants to drive and where you think it ought to drive. Now I want to talk to you about Pilotnet. The fact of the matter is, when we're driving, we don't do any Newtonian physics. When we're driving, we're not doing any calculus. When we're driving, we just drive. And so the question is, how do we get a car to just drive? And what we're going to show you is this. This is BB8. This is the latest version of our network, and we've been teaching it how to drive. Now remember this. BB8 has no detection networks inside. When BB8 is driving, it's doing, we didn't tell it, detect a cone, detect a lane, detect a post, detect a fence, detect cars, detect the absence of roads. We didn't tell BB8 anything. We just drove. We drove and drove and drove and drove and drove and drove, and BB8 imitating us. So what BB8 is going to do is imitate us. So the question is this: when we're driving, what do we see, and why did we do it? It turns out we don't have to describe it using algorithms. We don't have to describe it using equations. We only have to do it over and over and over again until BB8 generalizes, it detected the features, and it generalizes what is driving behavior. Ladies and gentlemen, BB8.
Oh yeah, good. The universal sign for auto.
There are no lanes here, ladies and gentlemen. That's barely a road. That is incredibly strange that the car did that.
I'm not touching it.
So cool.
No math. Just imitation. And then learn how to drive in the dark.
Got it.
What do you guys think? Autonomous machines. The thing that's really cool is this. I want to show you what's in BB8's mind. Is that okay? The question is, what did it see? The question is, what did it see? And so we just started driving, and eventually it learned how to drive just like us. Okay? It learned how to drive like us. The question is, what did it see? What are the things that it saw that it learned and generalized and eventually say, these things matter to driving? These things matter to driving. I think you'll be kind of surprised. Those sparkles are BB8's AI neurons. That's what's firing on this video. And look, it's kind of interesting. It's looking at that corner because that particular car is kind of closer to us. And every now and then, it checks the car in front. And it checks the car to the right. Every now and then. It's always looking at the lanes, making sure I'm staying inside it. Everything else that's not lit, wherever there's no sparkles, non-information to BB8. These are the things that it figured out that were important to its driving behavior. And then as a result, it just stayed in the middle of the lane all by itself, did no calculations, because it knew that largely when we drove, we stayed in the middle of the lanes. It knew that when we drove, when there are no lanes, we stayed in the middle of the road. And it recognized how to discern a mud road, a dirt road in the dark next to bushes. That we don't seem to drive over bushes. We seem to drive over the dirt road. Okay, ladies and gentlemen, BB8. So today we're announcing that DriveWorks that we talked about in the beginning of the year has made enormous progress, and we're in the process of packaging all that. Our strategy with DriveWorks is this. Drive PX and DriveWorks is an open platform. It's an open platform. It's an open platform that Tier 1 OEMs and Tier 1 ODMs and Tier 1 OEMs and car companies have the ability to pick off the pieces that they would like to use or the pieces they would like to replace. And together, we will work together as an industry to move autonomous driving forward. DriveWorks is an open platform. We have reached Alpha 1. As you know, that this is going to be an area of research and development for years to come. And even though we're going to see some self-driving cars get on the road here in the next year, or no more than next year and no more than the next couple of years, we're going to continue to enhance the software. Today, we're announcing that DriveWorks Alpha 1 will be released to our early partners in October. After that, of which they could use pieces that they like, pieces that they would like to replace, and after that, we will update it every 2 months. Just as we continue to learn as humans, our car will continue to learn, and the network will get better and better and better. Considering what we've achieved in just 1 year's time, imagine where we would be in another couple, 2-3 years. DriveWorks Alpha 1. Well, the number of autonomous vehicles on the road are increasing, and we're working with some 80 companies, 80 partners around the world, one after another over the next several months, the coming year, are going to be revealed. I think that the vision of having an AI computing platform, by which cars could be built on top of, that has the ability to do perception and sensing, localization and reasoning, planning and driving. The ability to have all of that on top of a deep learning platform is really quite the right answer at this point. And we're seeing just really, really rapid developments across all of our partners. Well, the work that you've